The atom. It's everything. It can be kind of intimidating, the idea of the whole universe relying on one fundamental particle. A long time ago, the concept of a fundamental particle, atomos, was introduced by the Greek philosophers Leucippus and Democritus. They theorized that everything was made of incredibly small, indivisible particles. For a long time, the fundamental units of the universe were a topic for philosophers, not scientists. This idea stuck around, and over a couple thousand years, it changed a little. Eventually, all of this led to quantum theory, a framework that finally gave us a mathematical way to describe what atoms actually do, not just atoms exist or electrons orbit the atom somehow, but here are rules, here are equations, and if you solve them, you get answers to match experiments with extraordinary precision. The centerpiece of quantum theory, the equation that governs how particles behave, is the Schrödinger equation. Today, we're going to solve it for the simplest atom there is: hydrogen. One proton, one electron, and the force between them. And when we do, we're going to get a number. That tells you exactly how much energy holds that electron in place. A number that was first predicted by Niels Bohr in 1913 using a patchwork of classical physics and early quantum ideas that frankly shouldn't have worked, but it did. And in 1926, Schrödinger's equation proved why it worked, rigorously, from first principles. That's what we're doing today. So let's start with energy. Here's something you already know. The total energy of a system is its kinetic energy plus its potential energy. That's true in classical mechanics, and it stays true in quantum mechanics. Just, it looks a little different. We call this total energy the Hamiltonian, H. It's just a fancy name for kinetic energy plus potential energy. That's all it is for now. One quick rewrite: instead of 1/2 mv squared, I'm going to use momentum. Since P equals mv, kinetic energy 1/2 mv squared is the same thing as P squared over 2m. In 3 dimensions, that's px squared plus py squared plus pz squared, all divided by 2m. Now here's where quantum mechanics does its thing. In quantum mechanics, momentum isn't just a number, it's an operator. Specifically, the momentum vector becomes negative I h bar nabla, where nabla is shorthand for take the derivative in every spatial direction, x, y, and z. I'm not going to justify this. It's from the wave nature of particles, and it's not necessary. Just take it as a rule. When we substitute that operator into our Hamiltonian and apply it to the wave function psi, we get the Schrödinger equation. The left side is how psi changes in time. The right side is kinetic energy plus potential energy acting on psi. It's still just total energy, kinetic plus potential. We've promoted everything to operators, and the thing we're solving for is a wave function instead of trajectory. One more move: when the potential V doesn't change with time, and for hydrogen it doesn't, we can split psi into a spatial part times a time part. The time part is always the same exponential, and it just carries the energy label. All of the interesting physics is in the spatial part, psi of r. This gives us the time-independent Schrödinger equation. This is the equation we actually solve. Pick a V, find the psi's and the e's that satisfy it, and for hydrogen, V is the Coulomb potential. So here's our potential: the Coulomb attraction between a proton at the origin and an electron at some distance r. Notice it only depends on r, the distance, not the direction. It's a little bit of a problem if we're working in x, y, and z because these Cartesian coordinates have no built-in concept of distance from the origin, but spherical coordinates do. That's literally what they are. So we're going to switch. I'm going to skip the details of how the Schrödinger equation actually transforms into spherical coordinates. It's a lot of calculus, and it's not where the physics lives, but this is what it looks like. Pretty ugly, but it's just the same equation. Kinetic energy plus potential energy equals total energy. It's just how the derivatives look in spherical coordinates. Now we pull the same trick as before. We guess that the solution factors. A piece only depends on the distance, r of r, times a piece that only depends on the direction, y of theta and phi. This is called separation of variables. It's the same trick we did before. When you plug this guess into the big equation, miraculously, the equation splits cleanly, One equation that only depends on r, and another that only depends on theta and phi. These are our radial and angular equations. Because of the separation of variables that we did, the two sides can only equal each other, or they can only equal a constant. We call that constant L times L plus 1. It's a little weird, but it's chosen deliberately because it makes the solutions come out cleaner. There's a key insight that we can notice here, and I want to point it out. The angular part, y, is the same for every spherically symmetric potential. It doesn't know about the Coulomb force. It doesn't know this is hydrogen, so the angular solutions are universal. All of the hydrogen-specific physics, the stuff that gives us our energy, lives entirely in R. That's where we're headed. But first, let's deal with that angular part. Okay, we're separating variables one more time. I think this is the last time. Y splits into a theta piece and a phi piece, and we're connecting them by another separation constant called m squared. The phi equation is the nice one. Its solution is just e to the im phi, a complex exponential. And here's the first place where quantization shows up. Phi is an angle. When you go all the way around, it goes from 0 to 2 pi, and you'll end up back where you started. That means that e to the im 2 pi has to equal e to the im 0, which forces m to be an integer. 0 plus or minus 1 plus or minus 2, and so on. It's not a rule we imposed, it just fell out of the math. The theta equation is harder. Its solutions are called associated Legendre functions. I don't think I have time to go through the entire derivations, but what matters is for these functions to be well behaved, L has to be a non-negative integer, and the absolute value of m can't exceed L. So for each L, m runs from negative L to positive L, giving you 2L plus 1 values. This is the spherical harmonics formula. The combined normalized angular solutions are called spherical harmonics. These are the things that give you the shapes of the orbitals. S orbitals are spherical because y00 has no angular dependence. P orbitals have lobes because ym1 does, and so on. Angular part is done, pin. Now for the part that actually depends on hydrogen and gets a little stickier. First, a substitution that will make things easier. Define u of r to equal r times r of r. This one move converts the radial equation into something that looks basically exactly like the one-dimensional Schrödinger equation, with an effective potential that has two pieces. The Coulomb potential pulling the electron in, and a centrifugal term pushing it out. Before we finish solving hydrogen, I want to show the technique on a simpler problem. It won't take too long, and hopefully it'll make the hydrogen solution feel a little bit more familiar. The quantum harmonic oscillator is a particle in a parabola. Different potential, same Schrödinger equation. After some cleanup, we're defining a dimensionless variable. I think it's the Greek letter xi, but I'm just going to call it a squiggle for the sake of the video. So, we define that dimensionless variable squiggle and an energy parameter k. The equation looks like this. Here's the procedure, and for this, just pay attention to the shape of it, not necessarily the details. First, we're going to look at the tails. When squiggle is huge, the equation simplifies to the second derivative of psi with respect to squiggle. The solution that doesn't blow up decays like e to the minus squiggle squared over 2. Then we're going to peel off that asymptotic behavior. We write psi equals h squiggle times e to the negative squiggle squared over 2. It's very fun to say. So h only has to describe what's different from the tails. Last, we assume h is a power series. H of squiggle is equal to coefficient plus coefficient squiggle plus coefficient squiggle squared. Plug it in and you get a recursion relation, a recipe that determines each coefficient from the ones before it. Now, the last step. If the series goes on forever, the coefficients start looking like the coefficients of e to the squiggle squared, which means h grows like e to the squiggle squared, which means psi grows like e to the squiggle squared over 2. Exactly the blow up we peeled off. The series has to terminate, and the condition that it terminates, that some coefficient hits 0, is a condition on k, which is a condition on the energy. Quantization isn't something we put in. It's the only way the math doesn't blow up. remember that because we'll see it again. First, we do some cleanup. We define a few rescaled variables to make the equation dimensionless. Kappa is related to the energy, and rho equals kappa r is a dimensionless radius, and rho naught is a dimensionless constant that also depends on the energy. Don't worry about it. It'll work behind the scenes. The point is that the equation is rewritten like this. Now we take the same kind of procedure as the harmonic oscillator, step by step. First step, look at the tails. When rho is huge, the 1 dominates everything in the brackets. The equation becomes second derivative of u with respect to rho, and it essentially equals u. So the well-behaved solution is u is roughly equal to e to the negative rho. When rho is tiny, the centrifugal term dominates. The equation becomes the second derivative of u with respect to rho equals L times L plus 1 over rho squared times u. And the well-behaved solution is u is roughly equal to rho to the L plus 1. Same as before, now we're peeling off 2 pieces. The behavior at infinity and the behavior at 0. Everything that's left, the interesting part, is v of rho. Now we get our power series. Assume v is a power series, plug it in, and grind through the algebra. You end up with a recursion relation. This is the hydrogen version of the harmonic oscillator's recursion relation. Different formula, same rule. It tells you how to build each coefficient from the previous one. If this series goes on forever, the coefficients start looking like 2 to the j over j factorial, which is the pattern for e to the 2 rho. That means v grows like e to the 2 rho, which means u grows like rho to the L plus 1 times e to the positive rho. It blows up, not normalizable, not physical. We define n equals big N plus L, so rho naught equals 2n. That's the quantization condition. Let's see what it gives us for energy. Recall that rho naught depends on kappa, and kappa depends on E. If we work backwards, this is what we get. And since rho naught equals 2n, we get... Okay, we have the energies, now let's assemble the actual wave functions. And that's the Bohr formula. Every allowed energy of the hydrogen atom, labeled by a single integer n. And it came from one requirement. The power series for the radial wave function terminates. Same logic as the harmonic oscillator. Quantization is the price of normalizability. Remember that we started with psi of r, theta, and phi. Technically we started with x and t, but skip ahead a little. We found out, by splitting them up into variables, that depends on n, l, and m. R, n, l, and y, m, l. We've already handled y, and for r, remember that u equals r times r of r, and u of rho equals rho to the L plus 1 times e to the negative rho times v of rho, where v is the polynomial that survived the termination. The polynomial turns out to be a known function called an associated Laguerre polynomial. I don't know how to say these right. Don't worry too much about the formula, just know that for each pair of quantum numbers n and l, there's a specific known polynomial sitting here. What we need to do now is normalize. The wave function has to satisfy this integral. I'll spare the actual integral. It uses an orthogonality property of the Laguerre polynomials in a change of variables, and we end up with this normalization, where a is the Bohr radius, and we already normalized the angular part. So putting it all together, the full solution is a wall of symbols, but every piece has a job. The exponential e to the r over an, the asymptotic decay we peeled off. It's why the electrons are bound. No, electron is bound. The 2r over an to the l, that's the behavior near the origin. The Laguerre polynomial, that's the power series, v rho, that survived termination. The Legendre function, and e to the im phi, those are the angular parts. The square roots out front, those are normalization constants that make the total probability equal to 1. Nothing here is arbitrary or made up. This was all from the math. We got 3 quantum numbers, each from a different part of the solution. Ew. N came from the radial termination condition. It labels the energy. L came from the angular separation constant. It labels the shape. And it's capped at n-1 because of how n is defined. If L equaled n, there'd be no polynomial left. N, big N, would be 0, meaning the series never even starts. M came from the periodicity of phi. It labels the orientation in space. And recall that the absolute value of m has to be less than or equal to L. For each energy level n, there are n squared distinct wave functions that all share the same energy. That's unusually high, more than the 2L plus 1 you'd expect from the angular part alone. And it's actually a special property of the Coulomb potential. There's a hidden symmetry behind it, but that's not for today. We started with the total energy, kinetic plus potential, and wrote it as an equation that wave functions have to satisfy. We switched to spherical coordinates because the potential only cares about distance. We separated the equation into an angular and radial part. The angular part gave us spherical harmonics, and the radial part, after we peeled off the asymptotic behavior and applied a power series, gave us a recursion relation that has to terminate. The termination condition is the quantization of energy, negative 13.6 electron volts. Not a postulate, not a guess, the only energy where the math doesn't blow up.